So our last talk today is, oh yeah, it's already here.
Yeah. Hello, everyone.
From Henning. Excellent. Good to see you. So greetings to Bremen. And Henning has prepared a talk about, well, actually the same thing as I've been telling in all the past years. We're going into more and more into a quasi-optic discipline. It's about direction finding, it's about beamforming, it's about detecting directions, and so on. Yeah. Since this is a pre-recorded talk again, I would like to ask my video team to play the pre-recorded talk. Go ahead.
So, hello, everyone. Thank you for coming to my talk. The talk I'd like to hold today is about my latest hardware project, software-defined radio project, and I will tell you a little bit about my coherent multi-antenna shortwave receiver and how I'm using it to do some direction finding for shortwave signals. Yeah, so my talk will be structured as follows. I will first give a short introduction of the motivation of this project. Then I'll present the hardware I developed. Then you will see some results from a field day, and then I will conclude my talk and give an outlook for a future possible project. So the motivation for this project. 1.5 years ago, I developed an add-on for the Raspberry Pi, which is loosely based on the QDX, or better say, inspired by the QDX. It's a switching mixer receiver with a stereo ADC for digitalization. And like the original QDX, square wave local oscillator is implemented using Scilab's SI-5351A. And it's also possible to transmit with this board, basically through RPI-TX and the corresponding GNU Radio block for that. Many thanks to Évariste and Jean-Michel, who are also frequent participants in the SDR Academy. Yeah, and I developed this board as an add-on for the Raspberry Pi, and I presented this project on a local workshop we held in 2024 in spring, locally organized by German Amateur Radio Club, our local district. And yeah, I got some really positive feedback. And one fellow OM was asking, wouldn't it be possible to scale up the system to support several antennas and then do some receive beamforming, like with a traditional Foursquare antenna, but more in a, say, phased array software-defined way to do it. And I was really intrigued by this idea, and so I started, researching possible components to implement this. And at the core of this receiver, of course, is the ADC. And so I was looking around, what ADC could I use? I was looking at multi-channel ADCs, which have sometimes rather complicated interfaces to interface with the Raspberry Pi, for instance. So my criteria were, apart from the digital interface, the ease of configurability. So either there had to be some existing Linux driver in order to configure the ADC chip, or even better, if there was pin strapping possible, just tying some config pins to defined levels in order to tell the ADC to do this thing or another thing. And of course, the price tag was also important criterion. So I had a look at a lot of different ADCs, and one candidate was the Analog Devices 7768. But I was originally planning to use this board in combination with a Raspberry Pi. It's an SPI ADC. It was not clear to me how difficult it would be to get this ADC running on a Raspberry Pi. So I went a different way because I realized that I would need to use an FPGA anyway. Then I said to myself, okay, I might as well then use 4 separate stereo ADCs. And this is how I did it then in the end. I chose Texas Instruments ADCs PCM 1820. Those are 192 kilosample 32-bit ADCs at an affordable price. And then I put them on a PCB in KiCad and duplicated basically everything 4 times. This is what you see in the top right figure. This is a rendering of the PCB, and basically it's 4 times the QDX receiver, and the 4 switching mixers are driven by the same clock synthesizer, so means we get a perfectly coherent system. The LO is asynchronous as well as the sample clock as well. On the bottom right, you see a screenshot of the synthesis software where I designed the FPGA design in, and basically it's a little block in the middle that is called 4I2S to AXI. And this block basically generates the clock signals for the ADCs. Those go out to the right. Here is outputs, and from the left, there are coming 4 serial data streams, one from each ADC. And then these are, say, merged together, and then I have this block that creates then 8 times 32-bit audio samples. And because stereo DAC, and so 4 times 2, 8 samples, and these are then just transferred via DMA into the processor core of the FPGA, and then everything is basically the same way I did it with my older SDRs I presented 3 and 4 years ago at the SDR Academy. This was basically how to do this, and then I ordered the PCBs and ordered the parts, and then I started populating the receiver board. And as in my last presentation in 22 that I held at the SDR Academy, I chose the EBATS 2405 board, which is a very cheap, repurposed Bitcoin mining controller board. If you're interested in the details, have a look at my presentation from 2022. And in the meantime, since 2022, others have also realized that this is a very nice board for experimenting. And there exists now a breakout board called the EBATS 4205 minimal breakout. The link, you can see it on the screen. And this is a very useful breakout board that allows powering the board with 12 volts and offers access to all the I/O pins using PMOD headers and standard 100 mil pin headers. I only had to modify it a little bit because I needed a clock for the audio. I had to botch in a crystal oscillator. It's barely visible on the board, but somewhere there in between. I removed the pin headers and soldered in the crystal oscillator instead. And I added a 5-volt regulator because the audio circuitry on this board requires 5 volts. So I needed to add this as well to this breakout board. That was the hardware. Then I went ahead and did the software part of the project. I realized that there wasn't at that time an IIO source block which supported 32-bit samples. Or maybe I was just too blind to find it, but I looked at the available block, GNU Radio blocks for IIO at that time, and there was no 32-bit source. So I wrote one myself. You can find it on my GitHub. So if you come actually when you're in a position where you need this kind of block, you can just download from there and compile it yourself. And you can see in the background how this simple flow graph looked like that I used for testing. This is the source block with the 8 individual ADC outputs, and for testing I used the fourth demodulator block. So these outputs here are I and Q of the fourth demodulator block, and then we combine this into a complex valued signal and plot it in time and in frequency domain. And this is what you see on the screen here. In this test, I set the local oscillator to 10 megahertz using a simple Python script that I wrote that chooses the correct values for the SI5351A to generate a quadrature clock that is needed for the switching mixer. And the signal generator, this very cheap one I'm using, I set this to 10.001 megahertz, means 1 kilohertz off 10 megahertz, and this is the signal that you see on the screen. Yeah, so you have one line at 1 kilohertz, and yeah, some alias, badly suppressed lower sideband here, but basically what I wanted to see, I saw this in this test. I saw a 1 kilohertz signal here in time domain and here down there in spectral domain. Talking about the Python script to configure the frequency synthesizer, I later added a feature to the IIO Linux driver that I published 2 years ago on my GitHub for the SI5351. It now supports a quadrature mode. That means you can now generate two clock signals exactly 90 degrees apart for a given frequency. And this is then used now for this receiver board. The flow graphs that I'm using now to receive signals, they command this quadrature mode and then configure the frequency you'd like to receive, and the rest happens automatically, that the LO is generated accordingly to this requirement of exactly having 90 degrees phase shift between each other. Yeah, that first test with the signal generator was successful, so then I tried something else. I hooked it up to my NFET half-wave antenna I have at home, and well, it worked on first try. You see here the result. FT8 receiver running. You see on the right the time domain signals, or the time domain signal in the middle plot and the spectrum in the bottom plot. And worked astonishingly well on the first try already. So that gave me confidence to complete the remaining 3 channels and then try out what I originally wanted to try to hook it up to a Foursquare antenna constellation. So added the 3 missing channels and then did a first try in my garden. I barely managed to get the 4 antennas on the lawn, but it worked by rotating it a little bit. The constellation, I was using 4 telescopic vertical antennas, the cheap ones you get from AliExpress. I hooked them up to the 4 SMA inputs of my receiver board, and then I did a first test. And you can see the resulting spectra and the resulting time domain signals in the bottom right plot. Doesn't look too spectacular. It's just 4 times more or less the same, but with slightly different noise and maybe in one plot the ratio of the height of the different spectral lines is a little bit different from the other ones. This is important later for direction finding. So it was really pleasing to see that I get for spectra which are similar but not really identical. So it was a nice sight in this case. Yeah. So then that was last June, and then later in September we had a field day scheduled. So I prepared an enclosure for my boards, for the FPGA board as well as the receiver board. And there you see there's now a different breakout board. It's a blue one. I did it actually especially for this multi-channel receiver, but I also prepared some connectors to maybe later extend this to a multi-channel transmitting system. So there are some coaxial connectors you see on the blue board. I will need them for clock purposes then later when I finish the transmitter. Yeah, what I also added to the system was a passive power over Ethernet injector and extractor in order to power this receiver from remote. Yeah, for instance, 20 meter of cable, standard Ethernet cable, and I can power the receiver over this cable. I don't have to use another power line or have a battery at the receiver. I can just do this remotely. This is very nice. The eBuds board has only 100 Mbit Ethernet, so you can use the cheap passive power over Ethernet that just uses the two unused twisted pairs for supplying power. And this is how these simple injectors and extractors actually do it. Yeah, and then September came, and I had the first opportunity to try out my Foursquare antenna under realistic conditions. And yeah, we every year in around September we have our district India, district Nordsee, has a camp on a camping site in Wildeshausen, northern Germany, and yeah, it's always a nice meetup and always the opportunity to try out things. And I thought this was the perfect opportunity to try out my receive array. Here's a close-up of the receive array. You see the vertical antennas here, 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 and here. Yeah, this is not exactly perfectly vertical, but it was vertical enough. You see here the radials. The radials are ribbon cables that I stranded, and then I have 8 radials each for each antenna. And then there are 4 identical cables of identical length that go to the enclosure, which you see here. This is the black metal enclosure where the PCBs are hosted, located in, and this is the Ethernet cable that is for data and power. Yeah, and then I was just recording some samples from the 20 meter FT8 band because I don't have a real-time solution yet. So as a proof of concept, I used offline processing. So now let's have a look at the algorithmic approach and the results I got from my experiment. Yeah, how to start with the signals you have recorded. Yeah, I have now recorded the data from the 4 different channels. They are sampled at exactly the same times. They are down converting using exactly the same local oscillator, means they are perfectly coherent. And now I did some offline processing using GNU Octave. And what I did basically is I calculated the auto power spectral densities, the 4 auto PSDs, and I calculated the 6 unique cross power spectral densities. You don't need to calculate all 12 of them because they are conjugate complex identical, so it's sufficient to calculate 6 cross power spectral densities. You can see them in the upper triangular submatrix here. I plotted the angle of the cross PSD because that's where the information actually is located in. And I plotted here the magnitude of the auto PSDs. So this is in dB, basically the spectrum you know from your SDR software. You can imagine it like that. But these 6 little figures here, they show basically the phase difference between a pair of antennas over frequency. So for instance, this is the phase difference between antenna 1 and 2. This is the phase difference between antenna 1 and 3. This is the phase difference between 1 and 4, 2 and 3, 2 and 4, 3 and 4. So, and of course, the phase difference vice versa is just minus the other phase difference. So this is what I meant by their conjugate complex identical. So you don't need to calculate those. Yeah, so I have spectra, okay, but now I need to isolate the individual stations. And in order to do this, I used decode FT8, which is the command line version of WJTX. Is it called like that? At least it's a command line version that just expects a wave file and will then print out the detected FT8 stations on the command line. And I used this and I parsed the output with GNU Octave. And then this is how I found the stations in the spectrum. So I have now a list of call signs with the corresponding frequencies. And what I now did is I looked up the auto PSDs and the cross PSDs for each station in each FT8 time slot by looking at the corresponding frequency. Yeah, I just read out. I picked the frequency info from the FT8 decoder and then looked up what are the actual PSDs, auto and cross PSDs for this particular frequency. And then I set up a matrix, so-called correlation matrix, which is 4 by 4, which now contains this information between, containing the phase differences and the received powers of the 4 antennas. And what you now can do is now you perform an eigenvalue decomposition. This is now advanced math. I don't want to go into much detail, but it's a one-liner in GNU Octave. And what I did is I picked the eigenvector that was associated with the largest eigenvalue, because that is basically the dominant transmission path, and normally the 3 other eigenvalues are much smaller and they don't contribute much. So you can restrict yourself to the largest eigenvalue and the corresponding eigenvector. This eigenvector now can be plotted in a particular way, generating a so-called a beam pattern. And what you basically do is you take a vector and now you use this vector as a so-called beam steering vector. Means when you look at this figure, means feeding these 4 antennas in the Foursquare constellation, feeding the same transmit signal. And if you do this, you get a radiation pattern, which looks like this. This is almost a perfect circle. It only has little dents here of 1 dB, but basically in the main directions, this is 0 dB. And you have little dents here, 1 dB, which is at 45 degrees, for instance. This is the beam pattern that you get when you feed the signals with identical You feed the antennas with identical signals. Yeah, means there is no phase shift between these antennas. You get this beam pattern. Now, what do you get when you feed these two antennas with a particular signal, with the same signal, but feed now these antennas with a 90-degree shifted signal? Sorry, this is a typo. This should be 90-degree here as well. 0, 0, 90, 90, it should read. What you now get is a propagation into 45 degrees into this direction here of 45 degrees. Yeah, because you have the phase shift, and for instance, into this direction, the signals cancel perfectly, and also in this direction, the signals cancel perfectly, and there's absolutely no radiated signal into these two directions because of the way you feed the antennas here. And now the idea is, if there is reciprocity, means if the antenna behaves exactly the same for transmitting as well as receiving, then this implies that when a wavefront, a planar wavefront, arrives here from 45 degrees, it will cause a phase shift in the received signals, which is exactly this here. If the wave comes from this direction, you will get exactly the same signals on these two antennas. You will get same signals on these two antennas, but they will be shifted by 90 degrees because we have here lambda, sorry, this should be lambda by 4, another typo, because we have lambda by 4 distance that the wave has to travel. So this means now the received signal is shifted by 90 degrees, the received signals of these two antennas compared to the signal from these antennas. And now you can, for every possible vector that represents the phase shift, yeah, this is a complex notation here, 1, 1, JJ is 0, 0, 90, 90 degrees. For each vector here, beam steering vector, you get a different beam pattern. And due to reciprocity, the same holds for the receive case. Means if we now plug in our largest eigenvector, the eigenvector connected to the largest eigenvalue, we will get a beam pattern, and the maximum of this beam pattern will relate to the direction where the wave actually came from. So means if we have, for instance, would find this phase difference in the if this was the vector, the eigenvector that we get from our algorithm, this would correspond to this beam pattern. If we would get this beam pattern 1, j, j, and -1 here, this would correspond to this pattern. And this vector here would actually correspond to this beam pattern here, because for instance, if here a wave comes directly from the right, it will detect it first at this antenna. Then after a little delay, it arrives at these two antennas at the same time. And at last, it arrives at this antenna. And it's equally spaced. If this is lambda by 4, sorry for the typo. If we have lambda by 4 spacing here, like in the Foursquare antenna, then you get these resulting phase shifts in the receive signal. Get 0 here, and then 64 degrees here, which is 0.707 times 90 degrees. And we get 127 degrees here, which is 0.707 times 180 degrees. And so we get a beam pattern which has exactly its maximum at 0 degrees, because that's where the wave came from. Yeah, okay, now let's apply this theory to the received signals from our field day. I wanted to compare the estimated directions to the true directions. So what I did is I found some code from a colleague of mine, a fellow OM from our club. He already wrote some Python code to calculate the angle of arrival, or say the angle between two arbitrary maidenhead locators. And this is what I used. I used this code to calculate the expected angle from where the plane wave is expected to be received. What was a bit tricky is I wasn't able to align my receive array perfectly in north, south, east, west direction. It was only approximately looking at Google Maps at the, say, view from the top and somehow aligning my antenna, somehow only telling from the way that the fence was oriented. So it isn't exactly north-south, but I guess it's good enough to get the impression. So maybe start with an example now. For instance, this station from Albania. Albania is actually southeast from northern Germany, and this is what you also see in this plot here. These are the different time slots in which ZA5G transmitted, and plotted here are the normalized beam patterns. They are, say, arbitrarily scaled. So this grid here is not exactly some particular value. It's just scaled to fit nicely into this polar diagram here. But you should only have a look at where the maxima are located, and this is actually here around 300 degrees, and the calculated direction from the Maidenhead locator was 303. So basically 5 degrees off, which I think is quite a good example, quite a good result in this example. Another station from Ireland came from the west, which is also meets the expectations. A station from Spain is from southwest, also with only 6 degrees of error between the measurement and the expected angle. Then there's Finland, which has a bit larger error here, but this may be due to the way the waves propagated on that day, because these beam patterns, they assume that, say, perfectly symmetric characteristic of the individual antennas, and you only plot the beam pattern exactly at 0-degree elevation, means in the plane, in the horizontal plane. And of course, depending on with what elevation angle the wave impinges on my array, this might result in a bit of error. So, but the general direction is correct here. Yeah, this was an Italian station which matched very, very closely with only 3 degrees of error here. A station from Ukraine had about 20 degrees error, which is still okay. But now we have a station from the US, from Texas actually, and now we get a very interesting result. We get really different angle of arrival in every pass, in every slot, FT8 slot, which is, say, varying between 240 and 310 or 315 degrees. Yeah, so it's really sweeping from here to here, or vice versa. Didn't have an exact look which way it swept. But you see that the direction of arrival, at least at my position, changed a lot over the course of a few minutes here. I can only guess that this was due to the fact that the angle was rather steep from with which the waves arrived at my receive antenna. So means some slight variations in the ionosphere maybe had a large influence on the, say, effective angle with which azimuthal angle with which the waves arrived at my location. Yeah, those so much now for the results of my experiments. I like to wrap up my talk now, and I was really pleased how well this estimation performed. Usually we get the general direction correctly. What I didn't do yet was combining the signals into one virtual receive signal in order to increase the SNR, because you could now, for instance, add up the individual wave signals from the 4 antennas, correcting the phase according to the phase difference with which the signal arrived at my station, and then create a received signal which is corresponds to what a virtual directional antenna would have received. The scheme is called maximum ratio combining, and this is usually done to increase the signal to noise ratio, and it works rather well. And this would be something to try out, how much the SNR improves by combining the signals with the correct phase correction and the correct amplitude weighting into one virtual receive signal. If you want to actually do this in a large scale, then it would be a good idea to implement this maximum ratio combining in an FPGA, directly in the FPGA, not have it running in real time, not have it running on a PC. This is something that you should aim for when you really would like to use the maximum ratio combining on a regular basis. And going one step further, I already mentioned a transmit system. You can actually, due to reciprocity, also use this phase information for transmitting. If I now use the corresponding beam steering vector as a literal beam steering vector, I would exactly transmit into the direction from which the signal came. Means I can directly use this eigenvector from the largest eigenvalue as a beam steering vector, and then it will automatically transmit into the direction of my QSO partner. But that, of course, implies that I'm able to control the phase of my transmit signal in a rather fine, granular way. And this is usually where it gets tricky, but I have already something in the works now. A scheme with which I can at least coarsely shift the phase of my transmit signals. This is currently work in progress, maybe something for next year's SDR Academy or the year after that. And there's one more thing I'm currently working on, which is another multi-antenna receive SDR, but with a different twist here. This is an 8-channel receive SDR, and basically it's based on the SDR that Pavel Demain developed, who also presented today in today's SDR Academy. And basically it's an 8-channel version of his SDR. It's an integrated 8-channel ADC running at 77.76 mega samples per second. And it's interfacing with the FPGA using very high speed serial LVDS lines, which was a bit of a pain to implement correctly in the FPGA, but I finally managed to, at least for 2 channels at the time being. And the idea, say the goal in the end, would be to also support several sessions in parallel. Like Pavel mentioned, you can receive different bands at the same time with his solution. My goal would be then to have also not transmit on on different bands at the same time, but also at the same time with different virtual directional receive antennas. Use different beamforming vectors for each session that actually receives one band at the moment. And that would be the goal to implement. I'm only at the very beginning at the moment. But yeah, I'm planning to put further work in that. And if you are interested in the progress, you can follow me on Mastodon. You see my account over there. And yeah, maybe see you then in the Fediverse. Thank you very much for your attention.
Yes, thank you very much, Henning, for this interesting talk. Yeah, arrays is always a very hot topic, very interesting technology. We've seen a couple of array talks today, and I think this is generally something we need to go into deeper in the future. There's one question. Yep, hold on.
What I find interesting about this approach is that if you transmit back along the axis of the calculated maximum signal, as we saw with the America example, maybe you go in the opposite direction. Because if you say your partner is in America, you rotate your antenna towards the US to take the short path propagation. But in this case, you are probably receiving over long path propagation, which is unusual and rare, but it does happen. And so instead of transmitting in the obvious direction, you would transmit in the most powerful direction, as it were, with the best signal. My question is actually, can you do this in broadband way? Does this only work if the antennas are exactly a quarter wavelength apart? Or could you say you could use the same array to transmit over or transmit and receive on 80 meters, 40 meters, 20 meters, 15 meters, 10 meters, and so forth?
Yeah, actually, in general, this works, but you might get some ambiguity regarding the beam pattern. So, for instance, you saw in one of my examples that sometimes the beam patterns are symmetric. That means you distribute, you send half of your power into opposite directions just because the physical spacing of the antennas doesn't really fit the wavelength that you want to operate on. And the opposite effect would be that your main lobes are getting very, very broad and you don't get that much antenna gain that you would like to achieve. So it actually only works as intended when you get this quarter wavelength spacing of the antennas. It will somehow work on other bands, but it's definitely not optimal.
Okay, thank you. More question? Yeah, okay.
Hi, Henning. I've got one question. You've actually used Foursquare here. And if I understand correctly, amateurs use Foursquare because basically you're getting a lot of gain for the number of elements. But if I remember back to my previous, I mean, it's a very long time ago that I've been to university. And in sonar and radar systems, they use planar arrays. Have you looked into that one, if that might be better for direction finding?
The big advantage of circular arrays is the symmetry. So it means with a circular array, regardless if it has 4 or 8 or 10 or 12 antennas, you get the same, say, sensitivity, no, not sensitivity, the same resolution, the same angular resolution into all directions. If you choose a linear constellation, either just on a line or something two-dimensional, you get preferred directions where you have higher resolution than in other directions. And say as a gut feeling, I would say that a circular array with, say, identical resolution all around is the most universal way to do it. If you know where your signal will be coming from, but you want to say resolve the very last degree, then you could use a linear array or even a two-dimensional one.
Okay, any more questions? No more questions. So, thank you very much. Henning, thanks for your insightful talk.
It was a pleasure.
So, dear audience, please give Henning a warm applause.
Yeah, the last talk of the day is always a bit of a problem, right?
Yeah, and I hope to see you next year, maybe again here in Friedrichshafen in person. I would appreciate it.
Yeah, maybe I can arrange it.
Okay, excellent. So, thanks a lot. It's 6 o'clock in the evening now, even 1 minute past, 2 minutes past 6 o'clock. This was the 11th SDRA. We've been here 11 years, which is a really long time. And we've had many, many interesting talks, many fantastic people here on the stage, many good speakers, great audience. This conference is foremost made up of an excellent audience and good speakers. So thank you very much for coming here. Thank you for attending. And I'll make it short this time because we're past 6 o'clock. Thanks for coming. And please come again next year. And now enjoy the evening here in Friedrichshafen and have a barbecue, have a beer together with the others down in the city or on the camping site. And I'm looking forward to see you again next year. Thank you to my video team, and thank you to all of us for following the channel. Thank you for being interested in what we're doing here. Thanks a lot. Bye-bye.